So hello everyone. In the last video we dealt about the Newton's law of motion and what is mechanics. So if I say what is mechanics, mechanics is basically the study of motion, right? So in the study of motions, what are we guys dealing about first is the free body diagrams, which will help us to solve various numerical problems. And mechanics is basically more about numericals and problem solving, right? Yes, you know, need to know the concepts, but numerical is something which numerical is something which is very necessary to have your grasp upon. Okay, so in this video what I'm gonna do is I'm gonna tell you some of the basic steps that you are going to follow, or we are going to follow while solving any type of questions in any type of question in mechanics or dealing with some free body diagram. Okay, so I'll be writing down few steps, just follow that. If you don't know what is free body diagram is like, let me give you a glance. If there is a table, okay, this is a table and it has a box lying on it. Okay, so what do is I zoom here. Okay, I zoom here and actually I zoom here and now see this box. Okay, this is the box which is I have zoomed. Now I'll see what are the various component of forces or various forces acting on this particular object or box which is kept on the table. So while analyzing this, we get to know that there is its mass into gravity mg lying downwards, then there is a normal force. Okay, so like this there could be many other components of forces within a body or acting upon a body. So let us move on the steps. So step number one would be reduce mass to a point mass object or symbol. Okay, like if there is a pendulum which is like swinging or making oscillations from here to here. So if there is a bob here, what I'll do is I'll make a point mass of it and then I'll justify its forces. Okay, so this is the point number one. Then we have the point number two is use the arrows to represent forces. Use arrows to represent forces. Okay, because what does arrows helps you to do is make you to get more understanding of the forces and to make it more clear in which direction the forces are acting. If this is a box and it is kept on a table, okay, this is a box and it is kept on a table, so what will be the forces acting on the box? What will be the forces acting on the box would be like this, mg, and another would be a normal. Okay, so this would be normal and this would be your mg. So while representing it with the forces, this would be, I'll consider this point to be this point, it is the center of mass or the point mass. Okay, so while considering these arrows of the forces, it will really help me to understand my problem very easily, because in this problem it is very easy for you to justify in which direction would be mg or which direction would be n. But in the problems like this where the body is kept here and it will be rotating to here and then it will fall, then making the direction of the forces would be very convenient to us in which direction the forces are acting. So marking your arrows to the very right direction of the forces makes a important role in problem solving. Moving to our third point, I hope you have got it. Moving to our third point would be choose the required coordinate system. Okay, choose the required coordinate system. Now what do I mean by choosing the right coordinate system? If you are in your first semester, then you are very much familiar with your Cartesian coordinate systems. Okay, the rectangular coordinate systems भी कहते हैं हम इसको, which is x, y and z, right? So this is one coordinate system, but there are other coordinate systems as well, which I will just write it for now and I'll explain you in the coming videos like what are the other coordinate systems we have. We have the Cartesian coordinate system, which is represented in x, y and z coordinates. Then we have the spherical coordinate system, which is represented by r, theta and phi. Okay, and then we have your cylindrical coordinate system, which is represented by rho, phi and z. Now you know that you have been using the Cartesian coordinate system from your early classes. Now, let me give you a bit of hints here. Spherical coordinate system is used when we are dealing with the problems in which the mass is rotating in a circular pattern. Okay, circular or a spherical pattern. Okay, if I may give you an example which you may be very much familiar, is again a pendulum. Now we have been solving this problem in the Cartesian coordinate system as well, but it is very easy to solve and this problem when we use the spherical coordinate system. And in spherical coordinate system we take this as r as the radial direction and this theta as the transverse direction. Okay, r is the radial direction and theta is the transverse direction. Now you might be wondering where is phi. Now this is our 2D problem right now. Okay, so there is not a third coordinate. When we'll study further, we'll be recognizing this phi angle also. And as for the cylindrical coordinates, suppose let's say if there is a plane. Okay, if there is a plane here and it is coming downwards, this is its ground. Okay, and it's coming downwards, so and it follows the path which is like this. Okay, now which follows a path which is like this, a helical path. Okay, now while solving this you can use the Cartesian coordinate system, but the problem that it's gonna create is the problem that we'll be solving would be more complex. So instead of using the Cartesian coordinates, we use the spherical coordinate system here. Okay, in these kind of problems we use spherical coordinate systems. This is the path that it follows. Okay, then we are going to use the spherical coordinate system. Now coming to the point number 4. Point number 4 says that make sure that the coordinate system is an inertial frame of reference. Okay, make sure the coordinate system is an inertial frame of reference. Inertial frame of reference. Now, what do you mean by inertial frame of reference? I have already told you in the previous lecture, but if I may brief, it would be like the frame of reference which are not in acceleration, okay, which are at a stationary place, stationary. Those are known as inertial frame of reference. Now, what do you do if there is a non-inertial frame of reference? So, in case of non-inertial, if non-inertial, then it is very important that you add a pseudo force in the direction opposite to the in the direction opposite to the acceleration. Okay, in inertial frame of reference we used to write F net, the net force acting on the body. Just wait a second. F net was equals to F, that was the force applying to the body, right? Here the F net would be F plus F fictitious or F pseudo force. So this here is to be made very necessary. This change is very necessary to understand the non-inertial frame of references. Okay, F net is equals to F, which is acting on the system, plus the fictitious force or the pseudo force that acts on the body. Now let us come to point 5. Point 5 says that resolve the forces along the coordinate axis. Resolve the forces along coordinate axis. Okay, now you have understand, you have made your point masses, you have marked your arrows, you have made the coordinate system, then you have also made it sure that it is a inertial frame of reference. What now you'll start solving and you'll resolve the forces along the coordinate axis. Now what do I mean when I say the coordinate axis? If this is an inclined plane, okay, this is an inclined plane and I have a object or a box that is lying on it. I don't know how to rotate it. So let us say we have a box here which is lying on this inclined plane. Okay, now when I'll resolve it forces, we have, this is theta, we have like what do we say, we have mg down, we have mg which is acting downwards, we have normal which acts perpendicular to the surface, then we have the components of mg, right? This side we have mg cos theta and we have mg sin theta. I hope you know the resolving of the forces and taking the components of the forces, and also if you might have not forget, there is a friction force. Okay, not fiction, friction force. Okay, now when you resolve it, what I mean to say, resolve it along the components coordinate axis, resolve it along the coordinate axis is that I suppose this is my y-axis and this is my x-axis while solving it. Okay, then we take it as along x axis. And what do I mean when I say along x-axis is I will be only taking the forces which are acting along x-axis. So F net would be equals to ma, and what is F net? That is mg sine theta, considering the block is sliding down, minus F is equals to, F is the friction. Okay, this is the force and this is in opposite direction, this F is in opposite direction, so I took a minus, is equals to mass times acceleration. That is, let us say this is my equation number 1, and along y-axis F net would be equal to again ma, and the box do not have here, let us see, you can not, let us see, you can all, you can see it yourself that there is no acceleration in the y direction. Okay, the box is stationary. So what I do is n minus mg cos theta is equals to 0, since there is no acceleration in y, which becomes n is equals to mg cos theta. Okay, n equals to mg cos theta, and mg sin theta minus f is equals to ma. Now equation 1 and equation 2 would play a major role in solving these kind of problems. If there are more forces, you will find more forces in these two components itself. Okay, so that was it, which was in point number 5. Now we have point number 6. Now what does point number 6 say? And also I wanted to say something. If there are polar coordinates, r theta, then this all problem will be solved in the polar coordinates itself. Okay, we are going to see the conversion of the polar coordinates to the Cartesian coordinates, or the Cartesian coordinates to the polar coordinates. You simply cannot use uh, dx upon dr to solve x square plus y square. Okay, dx upon dr, where x is equal to x square plus y square, or let's say d, not x, like d theta upon dr, again theta is not a variable, dm upon dr, when m is equals to x square plus y square. Okay, for the polar coordinates, if the question is given in the polar coordinates, we have to change it, we have to use the polar coordinates. Okay, we cannot use x, y and z, then we have to use r and theta. Okay, we'll be seeing how do you convert from the Cartesian to the polar coordinates and from polar to the Cartesian coordinates. Okay, you simply cannot use d by dx of r or d by dx of theta in the polar conversions. Okay, we'll see it in more detail in the coming lectures. Now point number 6, moving to the point number 6, kinematic equations can be applied only when acceleration is constant. Okay, what are kinematic equations? You are very much familiar with the kinematic equations. Kinematic equations are applied only when the acceleration is constant. Okay, only when acceleration is the constant, then only we are using the kinematic equations. So what are the kinematic equations? We have v is equals to u plus at, which we have studied in class 9th, and v square is equals to u square plus 2as, and s is equals to ut plus half at square. Okay, so this is used only when acceleration is constant. So this is it all in the 6th point. Moving to point number 7 is when more than when more than one object is involved, when more than one object is involved and interacting with each other, use the Newton's third law. More than one object is involved and interacting with each other, use the Newton's third law. Okay, if there are two bodies which are interacting with each other, you know what happens. There is a equal and opposite reaction, right? Equal and opposite reaction, which is the Newton's third law. So these are all the points which are necessary to solve or to approach a problem in mechanics. Okay, let us quickly revise what did we guys study, or let's take a quick summary. Step reduce. So the steps to follow while approaching the questions is: number one, you reduce the mass to the points mass or different objects. ठीक है ना? reduce mass to a point mass object or symbol. हम किसी बड़े मास को point mass पे represent करेंगे. Then we are going to use arrows. Okay, use arrows to represent our symbol. Then we have to choose the right coordinate system, that would be spherical, Cartesian or cylindrical. Then we have to make sure that the coordinate system is an inertial frame of reference, and this is very important, that if it is not inertial, use the pseudo force in the direction opposite to the acceleration. Okay, so when there is non-inertial frame, what do we have? We get our force equation, or we can say we have to add a pseudo force in our net force acting on the body. Then what do we do is, when we have find our forces and taken our coordinate systems, we need to resolve the forces in the coordinate axis, along x-axis and along y-axis. Then these are the only steps that most of the problems you'll solve. After resolving the forces, you can simply divide, multiply, add or subtract the equations to get the desired answer. Now we also have kinematic equations, which we apply when the acceleration is constant. Okay, and also whenever there are two or more objects involved or interacting with each other, use the Newton's third law, like we did in the case of the table, or we will be doing in the case of pulley or something else. Okay, so this was it for this lecture. Next topic, I'll be teaching you case studies on the various objects that we can get in the numericals. See, mechanics is basically more about numerical problems and getting an understanding of the concept while solving the numericals. So we'll be dealing with more and more numericals in this lecture series, which will help you to grasp a good to have a good grasp on mechanics. So with this I wind up. Thank you.